When a strong acid dissociates, it splits into H plus ions and the acid's conjugate base. In the case of HCl, it splits into H plus and Cl minus. Cl minus is the conjugate base of HCl. In the case of nitric acid splits up into H plus and NO3 minus. The NO3 minus is the conjugate base of HNO3. With strong bases, like sodium hydroxide, you split up into a metal cation and OH minus. In the case of sodium hydroxide, you split up into OH minus and sodium hydroxide's conjugate acid, Na plus. When strontium hydroxide splits up into its ions, it splits up into OH minus ions and strontium hydroxide's conjugate acid, Sr2 plus. Any conjugate of a strong acid or a strong base does nothing when you put it into solution. What this means is no conjugate of a strong acid or base will have any influence on the pH of a system because it will not interact with the water. Cl minus is the conjugate base of a strong acid, but it has no effect on the solution. If Cl minus was going to react as a base, it would react as follows. But this clearly doesn't happen. Chloride ions don't react with water to give HCl and OH minus, because any HCl and OH minus that were present in solution together would automatically react to give you water and chloride ions. The K value for HCl is so large that it would automatically dissociate again. So this reaction does not happen. And for a similar argument, the nitrate ion does not have any influence on pH because it does not react with H2O. And similar things happen for the Na plus and Sr2 plus ions. Any conjugate of a strong acid or base has no effect on pH. On the other hand, the conjugates of weak acids and bases do have an effect on the pH. When you have weak acids like acetic acid or hydrofluoric acid, their conjugates are basic. And this happens because their bases react with water. When a weak base's conjugate reacts, it has an acidic effect on the pH. We can apply these concepts to determining whether or not a salt will have any effect on the pH of a solution. And we can do this by using a couple of rules. The first is that cations always make a solution acidic, and anions always make a solution basic. The second rule is that rule number 1 doesn't apply if the cation or anion could have come from a strong acid or base. And we can put this into practice doing a couple of examples. Our first example is NH4Cl. NH4Cl is a salt. If you put it into water, it will split up into its ions. Those ions are NH4 plus and Cl minus. And we can use our rules to determine whether or not the whole thing will be acidic or basic. So using rule number 1, cations are acidic, anions are basic. We have a cation, we have an anion, so we have one part that's acidic and one part that's basic. So it's really kind of hard to tell whether or not the overall solution will be acidic or basic. So we move on to rule number 2. There's no effect if the ion could have come from a strong acid or base. So let's look at our two ions. Ammonium, the NH4 plus ion, could have come from a weak base. That is, NH4 plus could be the conjugate acid of a weak base, ammonia. It's not to say that it is the conjugate acid of that base, but it could be. With the chloride ion, the opposite is true. It could be the conjugate base of a strong acid. So if chloride could be the conjugate base of a strong acid, according to rule number 2, it would have no effect on the pH. If you have something that contains an acidic component, the NH4+, and something that has no effect on the pH, the chloride, the net effect is going to be acidic. So if you put ammonium chloride into solution, that solution will be acidic. For our next example, let's look at sodium fluoride. When you put this into solution, it'll split up into sodium ions and fluoride ions. And from here we apply our rules. Cations are acidic, anions are basic. So we have an acidic part and a basic part, and then we go to rule number 2. There's no effect if the ion could have come from a strong acid or base. The sodium ion could have come from sodium hydroxide, which means it could have been the conjugate acid of a strong base. So there'll be no effect. The fluoride ion could be the conjugate base of a weak acid. That is, it could be the conjugate base of hydrofluoric acid. And that means that rule number 2 doesn't apply, so its effect is determined by rule number 1. Anions are basic. So again, we have a situation where one component has an effect and the other component doesn't, and in this case, our net effect is basic. There are 2 remaining combinations that are possible. In the case of NaCl, you have Na plus ions and Cl minus ions. If you follow the rules above, you'll find that neither of these ions have any effect, and therefore sodium chloride solutions should be neutral. With NH4F, you have NH4 plus ions and F minus ions. If you follow the rules above, you'll find that one component is acidic, one is basic, and that means it's a little bit harder to decide whether or not the final solution will be acidic or basic. And to determine this, you have to look at the relative strength of NH4 plus as an acid and the relative strength of F minus as a base, which would involve finding their Ka and Kb values.